Start recording. Linear discriminant analysis for a single predictor variable. This is what we've been focusing on these past 2-3 sessions. Section 4.4.2. The context is chapter 4, classification models. Classification models, the response variable, the output, takes on two or more classes. We're taking the simplest case where the relationship between the response variable, the y, is against a single predictor variable. That's what we mean by p equals 1. P counts the number of predictor variables. We're going to try avoiding another session where it's mainly repetition. But I think yesterday's recap, at least I found it very useful to just find my bearings in terms of how we're using Bayes' theorem. As with everything else in this book, for instance, chapter 3, the goal remains making a prediction based on one or more characteristics of your input data, your observations. Think of people, think of companies, countries, armies, you name it. You know something about something, and then you want to make a prediction in terms of another of its characteristics. And that characteristic could be numerical or non-numerical, qualitative. Chapter 4 is focusing on on making predictions which take on qualitative, I mean, let's call them values. When we say values, strictly speaking, that's a number, but they take on qualitative levels, will be one way of putting it. And Bayes' theorem needs the probability, the overall probability that the observation is class K, irrespective of characteristics, as well as all the other probabilities for each other possible class. And the book says that's not too difficult to estimate these green probabilities, these overall probabilities. What does get a lot harder is the FKs, the FK of X's. What is FK of X? That's like the pink, but the other way around. So the blue is the probability. And yesterday we took height and biological sex. So we said the probability that height is so many centimeters, given that we know the biological sex of the observation. And hopefully you found that example useful. I think it was probably, we spent one session is probably just the right amount of time to see that we're really on the same page when it comes to these ideas. As always, if there are questions, do let me know. And these videos are being uploaded. I would encourage you to watch them maybe at 1.5 speed. I typically speak quite slowly. So at 1.5, that means it's going to take you a lot less than an hour. It will take you maybe, I don't know, 40 minutes at 1.5. And the very final thing that we said, and we kind of started doing it in Microsoft Word, but I think I'm going to abandon that line of inquiry. that we're trying to maximize. We're asking ourselves which k maximizes the probability that the response is class k given x. The probability that the response is class k, seizure, drug overdose, epileptic, whatever, given one or more. Well, over here it's one characteristic, right? P is 1. And the result appears to be that which k maximizes that probability? It's the one that gives you the largest value for this expression. So what we're saying is that if you're working with 3Ks, you will perform this calculation 3 times, once for seizure, once for stroke, and a 3rd time for overdose, whichever one of these Ks, think of them as K equals 1, K equals 2, K equals 3, whichever one of these gives you for a specific x, right? For a specific predictor value, for a specific x. So for each x, you calculate what we're denoting by delta kx, whichever of these k's gives you the largest delta k of x, you then classify that x under class k, and you're done. That's how your model is going to work. We're taking, if I continue reading, we're going to take an example where k is 2. Now do remember where k is 2, we said we can simply use logistic regression, but the same principle is going to apply for any number of classes, making this a bit more perhaps flexible than logistic regression. So k is 2 will delete, for example, overdose. Trying to get this arrow, it's proving, yeah, there we go. And we're also going to, this is just an example. We're also going to take that the overall probability of seizure is the same, is equal to the overall probability of stroke, so 50% and 50%. Then the Bayes classifier assigns an observation to class 1 if all this. I would like to see this in Word, if you don't mind. Gives us a better idea. By the way, speaking of, let me just, I think yesterday I got my logs wrong when RStudio, going to share it right now. Give us a few seconds, please. Where is it? Well, it's not this word file, right? No, that makes a difference. I mean, all I need to do is paste, but here we go. Let's see, what are we saying? What are we saying? So you will assign the observation. Think of it as observation X. You will assign. We shall assign x to class 1 if delta 1 of x is greater than delta 2 of x. Now, delta 1 of x is x times mu1. We're assuming the same variance. The variance is sigma squared. It's the standard deviation squared. Minus mu k squared, but this is 1 all over 2 sigma squared plus log pi 1. And it's not going to take too long now to change this into 2. So this is the second calculation for class 2. And we're asking, when is delta 1 x greater than delta 2 x? Right. Now we said we're just going to assume for simplicity that the pi's are 50%, meaning we can subtract log 50% from either side. We can multiply throughout by sigma squared. Sigma squared is always positive, so no issues with the inequality relation. And that leaves us with, is it easier to type, not just type it? This leaves us with, why don't I multiply by 2 sigma squared immediately? And we get this, and we get same thing, but with a 2. And if we tidy things up, we get 2x mu1 minus mu2. It's starting to resemble what the text has. Is greater than this minus this. So this is one situation where we only have 2 classes, class 1 and class 2. We said, let's say, seizure and stroke, both with the same overall probability, pi. And now we're asking, for which x's is delta 1? Excuse me. Just gonna. Sorry about that. For which x, which values of x would be classified into class 1? It's those x's that satisfy this inequality. Right. So, do we now make x subject of the formula? I think so, right? So we can now solve for x. It's a bit of difference of 2 squares over here, meaning I don't know how much of the work you'd actually like me to write, but it's going to look like this, correct? Which now gives us simply the mean of the means. The mean of the means. So for, but this is still an inequality, isn't it? Sorry about that. Like that. So we shall classify x into class 1 if it's greater than the mean of the means. Otherwise, class 2. The text is using quality because it sort of switched gears from speaking of classifying into class 1. It's now discussing the decision boundary. And let's see. An example is shown in the left-hand panel of 4.4. This is what we used for most of yesterday's meeting. The two normal density functions that are displayed represent two distinct classes. What we took yesterday as an example, what we used male and female for. Two classes. The mean and variance parameters for the two density functions are mu1 is negative 1.25 and mu2 is 1.25. So negative 1. That doesn't quite. Actually, it might be right because -1 is where I'm placing my cursor. Okay. And the same variance. So sigma 1 squared and sigma 2 squared, both 1. These two densities overlap. And so given that x is equal to x, there's some uncertainty about the class to which the observation belongs. If we assume that an observation is equally likely to come from either class, that is pi1 is equal to pi2, is 50%, then by inspection of 4.14, this thing over here, we see that the Bayes classifier assigns the observation to class 1. If x is less than 0, we're just taking the mean of these two means, and that's clearly 0, and class 2 otherwise. Note that in this case, we can compute the Bayes classifier because we know that x is drawn from a Gaussian distribution within each class, and we know all of the parameters involved. In a real-life situation, we are not able to calculate the Bayes classifier. So, well, I mean, we're kind of interested in the real-life situation, aren't we? So there's going to be probably some kind of estimation that we're able. So maybe the estimation comes into play when we start discussing this figure on the right-hand side. But on the left, your Bayes decision boundary is the vertical line x equals 0. If the x value, and we said yesterday x could be height, for instance. I mean ignore these negative values, but x could be height. So you'd classify anyone shorter than 0 as class 1, anything taller than 0 as class 2. In practice, even if we are quite certain of our assumption that x is drawn from a Gaussian distribution within each class, we still have to estimate the parameters mu's, pi's, and sigma squared. The linear discriminant analysis. Okay, so this is actually when it's only now that we're discussing linear discriminant analysis. This is going to be an approximation for the Bayes classifier. LDA method approximates the Bayes classifier by plugging estimates for pi k, mu k, and sigma squared into 4.13. So we're retaining this, but in real life, you don't exactly know mu, nor sigma, nor the pi's. But apparently, what we're going to do to estimate mu k is is this. So this gives you an estimate of mu k that you can then use for the base classifier. And this gives you an estimate for sigma squared, which again, you'll then use for the Bayes classifier. And I don't know if you want to have a look at, the green is extremely simple. The green is just secondary school mean, you know, where you add all the values and you divide by the total frequency. Total frequency is this over here. Of course, it only counts the number of observations that have class K. And you add each, so if this is height, to go back to yesterday's example, for males, you take the mean male height, and then you take the mean female height. Yellow looks maybe a bit more intimidating. It's a double summation. We don't need to go into double summations. We'll just take the book's word for it. But it is roughly what you would expect. Meaning what? Meaning to get an estimate of variation within your data, you look at the difference between each data value and the mean. It gives you a good idea of the variation. Where n is the total number of training observations and nk is the number of training observations in the kth class. So adding all the nks would give you n, correct? The estimate of mu k is simply the average of all the training observations from the kth class, while sigma squared can be seen as a weighted average of the sample variances for each of the k classes. Sometimes we have knowledge of the class membership probabilities, pi 1 to pi k, which can be used directly. In the absence of any additional information, LDA estimates pi k using the proportion of training observations that belong to the kth class. Very, very, very simple. Pi k, so pi seizure is number of patients in our data set who did suffer a seizure divided by the number of patients. So I think next to everything we did yesterday, I feel that this is more straightforward. As always, it is great to hear your own questions or commentary. The LDA classifier plugs the estimates given in 4.15, 4.16 into 4.13 and assigns an observation with characteristic X to the class for which delta hat K of X is largest. The word linear in the classifier's name stems from the fact that the discriminant functions, delta hat K, are linear functions of X, as opposed to a more complex function of X. Think of your trigonometric, your logarithmic, it's just linear in X. The right-hand panel of figure 4.4, so now we're back here, and with this data, you can calculate your mu hat 1, your mu hat 2, your sigma hat squared, and even this if necessary. The right-hand panel of figure 4.4 displays a histogram of random sample of 20 observations from each class. So we're back to 50%, right? 20 observations from each class. So there are 20 males, if you choose to continue using that example, and 20 females. To implement LDA, we began by estimating pi k, mu k, and sigma squared. We then computed the decision boundary, shown as a black solid line that results from assigning an observation, was that black line. All points to the left of this line will be assigned to the green class. And now that's the model in action. The model is looking at the single characteristic, this x, or think of it as x1, if you will. All you are telling the model, you are giving it one characteristic. You are giving it, for instance, what the book has been taken as x, call it x1, and the model will then classify based on this boundary line. So if you give it, for example, -2, anything with a -2 will be classified into the green class, otherwise into the pink class. Now, don't expect your model to get it right each time. And we kind of already had a brief look at this a couple of sessions ago. This pink observation, the model will classify it incorrectly as green. These three green observations will be incorrectly classified as pink. Now, the better the higher the predictive power of the model is, the less incorrect classifications you will have. All points to the left of this line will be assigned the green. In this case, the n1s are 20. The n1 and n2 is 20, so we have the same pi1. As a result, the decision boundary corresponds to the midpoint between the sample means for the two classes, which is very similar to what we had earlier in the theoretical version of what we're doing over here. The figure indicates that the LDA decision boundary is slightly to the left of the optimal Bayes decision boundary, which instead equals this. How well does the LDA classifier perform on this data? So now we're kind of looking at similar to what we had in chapter 2, like mean squared error. But the training mean squared error. Since this is simulated data, we can generate a large number of test observations in order to compute the Bayes error rate and the LDA test error rate. These are 10.6% and 11.1% respectively. In other words, the LDA classifier's error is only 0.5% above the smallest possible error rate. This indicates that LDA is performing pretty well on this dataset. So that's the error rate. So the error rate is, think of these 4 incorrectly classified observations from within the training dataset itself, 1, 2, 3, 4, and 4 out of the 40 observations. That's roughly, well, it's exactly an error rate of 10%, which is reflected in these two percentages over here. To reiterate, the LDA classifier results from assuming that the observations within each class come from a normal distribution. Oh, I see. So LDA, you're always assuming normality. For each class, for each K class. With a class-specific mean vector and common variance sigma squared. and plugging estimates for these parameters into the Bayes classifier. In section 4.4.4, we will consider a less stringent set of assumptions by allowing the observations in the kth class to have a class-specific variance. So what we're saying is for the time up to this point, we've taken the same variance for each class. The variance is, just think of this wrong. Think of the width of each. These are known as probability density functions. The smaller sigma squared is, the narrower the sort of the distance between this part of the curve and this part of the curve. Now, linear discriminant analysis for p is greater than 1. We now extend the LDA classifier to the case of multiple predictors. To do this, we shall assume that x is equal to, so we don't just have x1 now, but x1, x2 until xp is drawn from a multivariate Gaussian, also known as a multivariate normal distribution with a class-specific, and it's no longer mean. Not mean. Look. Not a class. Oh, interesting. They use vector over here as well. I'm actually, I missed this word earlier. Each class can't, yeah, I mean, yeah, but this vector would just be one value, right? Mu k. A class-specific mean vector and a common, instead of a common variance sigma squared, a common covariance matrix. Right. So it's no longer a single value. It's going to be a matrix. So we're going to use a matrix to describe the variability within the distribution. We begin with a brief review. Well, maybe for some of us, this is a review. Let's see. If necessary, we'll cut our losses and maybe skip this section, although we probably are going to need it for future chapters. We begin with a brief review of such a distribution. The multivariate Gaussian distribution, by the way, we're going to be working with things like these two over here. Assumes that each individual predictor follows a one-dimensional normal distribution. I think we need to go into the browser now. Let's see, just close these. Let's look at yeah, that's exactly it. That's exactly it. Look. So what we've had until now has been a single predictor variable, for instance, y. Well, maybe why is usually reserved for our response variable in the book. So let's call them x1 and x2. X1 and x2. So in the previous section, when we only had one predictor variable, say x2, we were looking at x2's probability density function, and we spoke of the mean and the variance. But now we have more than one predictor, so let's just assume two predictors. Each one, so the first assumption is that each one has a Gaussian density function. So the histogram is, think of it as bell-shaped, it's kind of symmetric, etc., etc. The same features that we've been discussing ever since we started these last few sections. Now, we're then going a step further, and we're kind of looking at these two predictor variables at the same time. And that would be the scatter plot over here. And we're going to get a surface. The more points there are, the higher the density, the higher the surface is from the, I don't know, from the floor. And this is what's going to give us this sort of like, I don't know, okay, I can't really think of what is that? Looks like this. It's not really a dome shaped, is it? But let's call it dome. This dome shaped distribution. So instead of speaking of area giving you the probability, you remember in Desmos? I think that was yesterday, when we were saying, for example, the probability of getting between 1 and 2. Now it is volume that gives you the probability. So the total volume under the surface, but above the plane, but above, above this plane, that's going to be 1. So that surface, that the volume enclosed between this dome-shaped surface and sort of the x1, x2 plane, that's going to be exactly 1. And then you start speaking of, for example, I could ask you, what is the probability that x2 is between these two values and x1 is between these two values. So what you would do, you would calculate the volume under the surface, but above that blue rectangular region. And that volume is the probability that x1 takes on a value between those two red lines, and x2 takes a value between those two orange lines. So hopefully this is making sense. It's just a generalization of the one-dimensional case. If it's 2 dimensions, we now calculate probability, or you think of probability in terms of geometrical ideas as the volume beneath that surface. Now, there's also a correlation between each pair of predictors. And the correlation is, for instance, over here, the correlation, you just draw like a trend line. The correlation is roughly this. See how it's elliptical, not circular? If it was circular, there would be no correlation, to my knowledge. But elliptical, it means that the two variables, x1 and x2, they do sort of should I say, well, they're correlated. What's another word for correlated? That if you know something about x1, then you kind of know something about x2. We usually take the example of voting patterns, right, or political beliefs. If you know a person is of a specific religious denomination, then you could say, okay, they're more likely to be in favor of this position or less likely to be in favor of that position. Two examples of multivariate Gaussian distributions with p equals 2 are shown in figure 4.5. Okay, so this looks like circular, this looks like elliptical. The height of the surface, no, this isn't, yeah, okay. It's basically correct. Might be simplifying. They're using height to avoid mentioning volume. So when you mention volume, that's kind of like integration. The height of the surface at any particular point represents the probability that both x1 and x2 fall in a small region around that point. It's not quite precise, but yeah, it's good enough, right? Just think of volume under the surface. That's closer to the true definition. In either panel, if the surface is cut along the x1 axis or along the x2 axis, the resulting cross-section will have the shape of a one-dimensional normal distribution. That's probably quite important. If you slice it, if you take a slice, just take a slice. If you take a slice, you will get a normal distribution. Sort of like conditional, right? Depending on where you slice. Maybe I should show you this in GeoGebra and Desmos. But how long would it take if we go into the browser? Is there an easy way of typing this formula? I mean, I want to avoid matrices as much as possible. So can you just give me the two-dimensional case? Maybe we just figure it out ourselves. I mean, how difficult could it be, right? And how are we doing for time? Yeah, so we're like, yeah, it's probably enough time. So what if I said e to the negative x squared plus y squared. Yeah, right? I mean, it's not that difficult to figure it out. So you see this? See this? Now what I'm going to show is the following. What are I'll tell you why I'm doing this. So one is the x-axis is which one's the x-axis? Let me just show you. Let me just show what's happening over here. Yeah. So this is the x-axis, there's the y-axis, and there's the z. Can remove this now. Now, how do you take a slice? It's actually really easy, but I'll show you the slice in Desmos. And we can even put them side by side. Okay. So look at this. Look at this. Uh let me fix x. So didn't I type in GeoGebra? Didn't I type negative x squared plus y squared? Of course, the Desmos cannot plot this. In fact, it tells us, yeah, we will take it as an equation, but because an equation that would be okay. That will give you a curve again. Now, if I take a specific x, call it a. If I take a specific okay, that's not going to work because Desmos wants. Okay, so I'll take a specific y. I'll take a specific y, and I'll tell you what's happening over here. So look. When y, you need to look at that as y. When y is zero, let me show you what you get over here. When y is zero, you get. You see this pink? You see this pink? That's this. And you get this normal distribution. Do you see it? Do you see it? Like that? Okay. Now this is the highest that it gets. If I take y is 1, or y is 2, or y is -1, all the slices are going to have a lower, their maximum point is going to be lower than this maximum point. Look, see? I'm moving along the green axis. Okay? Until it's practically flat. The more you zoom in, it won't be identically equal to 0, but you can make it as close to 0 as possible. I don't know if this helps. By the way, if you're doing partial differentiation, all this, university for one of your actuarial exams, this is how you should look at differentiating a surface. You fixed one of the variables, you fixed y, and then then it sort of becomes just A-level differentiation. Okay, so hopefully we now feel comfortable with the statement. In either panel, if the surface is cut along the x1 axis or along the x2 axis, the resulting cross-section, but the cross-section is just going to be a curve. The resulting cross-section will have the shape of a one-dimensional normal distribution. The left-hand panel of figure 4.5, this one, illustrates an example where both variables have the same variance. Variance means sigma squared, and their correlation is 0. The correlation is 0. This surface has, oh, okay, they're using Bell as well. This surface has a characteristic bell shape. However, the bell shape will be distorted if the predictors are correlated. So think of correlation as what we saw over here. Like over here, you have like this correlation. Or have unequal variances, as is illustrated in the right-hand panel of figure 4.5. In this situation, the base of the bell will have an elliptical rather than circular shape. To indicate that a p-dimensional random variable x, so this is a vector, okay, has a multivariate Gaussian distribution, we write x has probability density, normal, and two parameters. We still have mu, but mu is probably going to be a vector. Yeah, a vector with p components. And instead of sigma squared, we're going to have what is called the covariance matrix. Here, the expectation of x, so just what you would expect from x, is mu, is the mean of x, and the covariance of x is this matrix sigma. It has nothing to do with summation. It's just Greek letter sigma. Is the p by p covariance matrix of x. Formally, the multivariate Gaussian density is defined by this function. Okay. So let's make it clear that it's the same as what we've been working with for the situation where you have just a single predictor variable. So this is not multivariate. This is just normal Gaussian in higher dimensions. So for example, think of what I did in Desmos. What I did in Desmos is roughly this, but this is more general because it's just p dimensions. Do we need to get into the mathematics? Maybe yes, maybe no. Right. This is a real number, right? That's a real number. 1 division by something to the p all over 2, the determinant of sigma square root. So all that's just a real number. What about this? Well, this is a real number as well, isn't it? Why? I think so, right? Why? Because this will be p by 1. It's a vector of p components. It's a column vector. This is the inverse of sigma, so that's p by p. This is the transpose of x minus mu, so that's 1 by p. And if you remember your matrices, you'll get this will be 1 by P, if you multiply these two first, and then you'll get 1 by 1. Huh. Right. So f of x is just a real number. Now that can't be right. Yes. Yeah. Yeah. It's just a real number. What isn't a real number is x. X is a vector. X is a vector. So all we're saying over here, we could maybe take a specific example at some point and even put it in Desmos. But what we're saying is that f of x, this f of x, it gives you the height of the surface, just like what I did in GeoGebra. If how do I get? I'd like to get the formula again. Anyway. By the way, if you're asking why is there all this, this is to ensure that the volume under the surface is exactly 1, which is why you'll have all these additional, this is just to scale it down. So depending on your values of x, for example, you have two values, which in GeoGebra was x and y, but in the book we'll take them as x1 and x2. For any value x1 comma x, for any pair of values x1 comma x2, 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 f of x1 comma x2 gives you the height above the surface, with the largest height, with the greatest height being over there. Okay, and really that's it. I think this is all we need to know for multivariate Gaussian distributions. Look, notice this time before we continue reading on. It's such a great book, isn't it? So over here we had two different classes. We had k equals 1 and k equals 2, pink and green, green and pink. Over here we have three classes, pink, orange, and blue. It's probably quite difficult to draw the three probability density surfaces. So instead, we've just drawn sort of the ellipse for each one. Notice that we're taking sort of the same kind of ellipse for each class, in the sense the variance, the correlation, the means are different. The means are different, right? So for example, the mean of the green is somewhere over here. It is this x value, comma, this x value. The mean of the blue class is somewhere over here, and the orange is somewhere over here. So they have different means. But it's the same ellipse, it's just translated. Similar to this over here. It's the same curve, but translated. So different means, but everything else is the same. And that's what's happening over here. And notice this decision, we're doing the same kind of thing with LDA, linear discriminant analysis. We're creating a decision boundary. So now the model is going to take the black And that's our 1 hour is up, so we'll just conclude on this. The model is going to take the black lines. Anything over here will be classified as blue. So what do you mean, anything over here? For these values of x1 and these values of x2, those observations will be classified as blue, seizure, stroke, drug overdose. These will be classified as green, and these will be classified as orange. And this is where we're going to stop.